I'm Alex Bigelow from the University of Arizona, and these critters and I are excited to present our Viz paper. The way that we think about data is really open-ended. If I gave the same data set to everybody watching this talk, we'd probably get a lot of different perspectives. Some of you might be more likely to think of the data in terms of points in space. Others might be more likely to think of data as a network. You could also think of most data sets in terms of set relationships. And no matter how you're thinking about the data set, on disk it might be something totally different like relational tables. These differences in data perspectives can matter a lot. We know that choosing a poor data abstraction in a design study introduces serious risks, such as building a system that doesn't actually support any real user needs. We also know that only considering one specific data abstraction can limit your creativity and influence your analysis. For example, as an undergrad, I once tried to use a force-directed layout as a really bad version of multidimensional scaling. And even though we eventually realized our mistake, it took weeks for everyone on the project to stop thinking about the data as this kind of network. On the flip side, considering alternative abstractions can have major creative benefits, like how the authors of Abyss Explorer reversed what they considered to be a node and what they considered to be an edge, and it led to some incredibly cool new network visualization techniques. So the way that you choose to think about your data is important. But there's still a lot that we don't know. In fact, we know so little about this that it's hard to even figure out where to start. Nebulous questions like, how malleable are data abstractions, aren't really the kind of thing that you can just drop into the scientific method and churn out knowledge. There have been recent calls in the visualization community to begin embracing different ways of knowing. In this case, with only a vague question, we can still engage in rigorous research. But what we do, and what we contribute, may feel a little bit different from the positivist research that we tend to see, or the kind of research where you're rigorously testing a hypothesis. Instead, our paper focuses on getting at better questions and discovering the blind spots in our own thinking. We want to describe phenomena for the purposes of generating and refining hypotheses. Our epistemological goals are interpretivist rather than positivist. To do this, we employ a technique called grounded theory. And as it hasn't shown up very much at Viz, here's a quick introduction to how it works. Although, for those of you that are familiar with grounded theory, please keep in mind that I'm glossing over a lot for the sake of time. The general pattern of our grounded theory investigation involves identifying codes, or specific observations of phenomena that arise while conducting various research activities. In our case, we engaged in theoretical discussions, performed ad hoc interviews, and conducted a survey. The choice of research activity is, in turn, informed by the codes as they evolve. As codes mature, they're typically grouped into categories and begin to form themes, or higher-level descriptions of phenomena. Eventually, codes and themes reach saturation, or a point at which researchers are confident that the codes and themes are unlikely to change very much, even if additional data were to be collected. This means that you've arrived at what is often called a substantive theory that describes phenomena with enough detail that it becomes much more straightforward to formulate hypotheses. And because it's grounded in real observations, you can have a better sense for whether the questions that you're asking will matter in the real world. In asking our how malleable is a data abstraction question, we wanted to learn from people who think a lot about both its theoretical and practical implications. To get a diverse group of perspectives, we focused on several different communities, including people from our local university, people at the Viz and Supercomputing conferences last year, and we also decided early on to engage with a local meetup group that met bi-weekly at a coffee shop, at a bar, and online, in an informal setting where people frequently brought laptops and asked questions about their code or data. This group included a very diverse array of data concerns, from bioinformaticians, paleontologists, and linguists from the local university, to designers, developers, and even vehicle mechanics in the local community. The meetup group in particular facilitated opportunities for many ad hoc interviews in the context of a real project with real data. We also designed and deployed a survey with each of these groups. As is kind of unavoidable in a study like this, we went into these interviews with a specific data abstraction typology in mind, or a way to make sense of and categorize the kinds of data abstractions that exist. It didn't take many interviews for us to realize that it's actually pretty rare for a dataset to fit cleanly in one category. For example, even if someone has an Excel spreadsheet, it's really common for things like full sentences or even nested JSON to exist inside its cells. To call something strictly a table, strictly textual, or strictly grouped is usually a little inaccurate, but an abstraction typology still gives us a way to start asking more targeted questions. Early interviews show that introducing a typology can expose latent abstractions, or a data abstraction that's meaningful and useful, yet undiscovered. If, for example, someone thinks about their data spatially and they also think about their data as a table, what happens if you introduce a concept that they don't normally think about, such as groupings? We designed a survey to simulate the process of pursuing latent abstractions. Using an abstraction typology with 6 broad abstraction types, we asked participants to describe any dataset of their choosing in terms of the categories that were the best fit, as well as describing their data in terms of a category that they felt fit the least. This wasn't a typical survey. Remember, our goal wasn't a positivist test that could lead to statistically significant numbers. What we really wanted was to find the blind spots in our own thinking. We wanted better questions, so we added some mechanisms for participants to critique the questions that we were asking, as well as the language that we were using. Instead of just adding a comment field at the end, we made it possible for participants to skip entire sections that they felt had strayed too far from being relevant or useful. We also added an interactive glossary where participants could suggest alternative definitions and terms. We've released the full visualized corpus of survey results, and they're archived on osf.io. Although we're mostly focused on the malleability of data abstractions, we're hopeful that this data will be useful to studies beyond our own. There's one result, however, that we didn't report in the paper, and it's not in our released datasets. To incentivize participation in the survey, we gave away stuffed plushies. And there was some interest from the Viz community as to which animal was most popular. So, as a result, exclusive to this talk, we're happy to report that foxes and crocodiles were the most popular. So popular, in fact, that we had trouble keeping them stocked. Although we ran out of foxes first, this introduced enough uncertainty that this unfortunately means we're going to have to leave this very important question for future work. After analyzing our interviews and survey results, we ultimately arrived at 24 codes. We don't have time for them all, so here are just a couple highlights. Our 8th code is that many people did not feel that what they work with counts as data. This comment was really common when we asked people to take the survey. People were even sometimes hesitant to describe their Excel spreadsheets as data, and we weren't the only ones that noticed this. 3 of our interview participants independently made this observation while reflecting on their experiences working with people that are new to data science. One participant runs a regular data science workshop in the humanities, but it gets very low attendance. It usually has about the same 3 participants. As we talked about why it can be hard to convince people that they're working with data, he noted that seeing information as data may take a certain level of creativity and a willingness to experiment and fail. Our 13th code is that there's wide variation in how people describe hierarchies. We ran into this ourselves while designing our survey. Even among the authors, we recognized that someone could describe hierarchies as partitions of space, as a special kind of network, or as nested sets. We questioned whether a tree and a hierarchy are the same thing, but concluded that they have semantic differences. So in the survey, we deliberately paired hierarchies with networks, with the word hierarchy chosen deliberately to encourage feedback. And it worked. One participant commented, "I find the separation of hierarchies and groupings to be a bit problematic for this domain. Many codes, such as diagnosis codes, exist in a hierarchy defined by metadata. However, it's quite common to refer to areas of this hierarchy as groupings." From these 24 specific codes, 4 major themes emerged. The first is that latent data abstractions are very common. Even people that are trained to look for latent abstractions, such as people in the Viz community, often miss opportunities to think about their data creatively. That said, the process of identifying an abstraction is an intervention with far-reaching effects. Although a lot can be gained by considering an alternative data abstraction, merely introducing a compelling new concept can have repercussions on the workflows and tools that people use, the science that they perform, and potentially how someone thinks. People have natural defenses against this invasive process. People are less willing to pursue latent data abstractions when the design of an existing abstraction is already fundamental to their workflow. One thing that seems to soften the blow is that introducing a data abstraction typology helps to focus reflection and communication about data abstractions at a level of detail that includes actionable information. As visualization researchers, we need to be transparent when we have an agenda, like when we want to identify data abstractions and associated tasks in a design study. Introducing an appropriate amount of theoretical background can, on its own, provoke creative thinking and help people to communicate things that they otherwise wouldn't. So what does all this mean for you? We've distilled the lessons from reflecting on our experiences as a list of 9 guidelines for pursuing latent data abstractions. Again, we don't have time to cover them all, so here's just one example. Create artifacts that document and convey abstraction details and demonstrate possible permutations. We discovered that even in discussion among the authors, there were times when we believed we were discussing the same abstraction, only to discover that we had completely different assumptions once we started drawing things or writing things down. Making ideas physical serves not only as a communication aid, but also as a method to explore the creative space of possible abstractions, as well as documentation for the decisions that you make. I'd just like to conclude with 2 parting thoughts. When you introduce a typology, one thing we discovered is that it's totally okay if it's imperfect. In fact, missing or inaccurate categories can be really useful because they can help people to engage with you at a theoretical level and explain important nuances about how they think about their data. That said, when you're preparing to discuss someone else's dataset, it's still worth the effort to try to prepare an explanation of the space of possible abstractions that's tailored for the person that you're talking to. For example, if someone has a rich mathematical background, the difference between physical space and an abstract mathematical space could be very important. But to someone else, that much jargon could be confusing and make them less likely to provide useful critique. One of the things that motivated this study was limited detail about data wrangling operations in published visualization research. We all do a lot of data wrangling, but rarely document the wrangling that we do as part of our publications. This isn't just important for reproducibility. Having more data about how we think about and work with data can teach us a lot. We're excited about recent efforts to recognize the reporting of data transformations as standalone research contributions, and expect that this will lead to better informed data wrangling tools and theoretical research. So that's about it. I'd like to thank my co-authors, our funding sources, and all of our participants, including many of you. And thanks for listening to this talk.